This is section 4.7, where we are going to go over Cauchy-Euler equations, also known as equidimensional equations. So a linear second-order equation that can be expressed in the form a t squared times y double prime plus b t y prime plus cy equals f, where a, b, and c are constants, is called a Cauchy-Euler or equidimensional equation. So this differs from our homogeneous and non-homogeneous stuff in the past by these t squareds, these t's. To solve homogeneous Cauchy-Euler equations, so that is if they're equal to 0 instead of having this non-homogeneity, we look for solutions of the form y equals t to the r. So let's look at this. If y is equal to t to the r, that first derivative, just power rule, bring that r down. R is just a constant here. And the second derivative is also fairly simple to take. If we plugged all these values in to this equation, we get at squared times what we got for y double prime plus bt times rt to the r minus 1 plus ct to the r equals 0. Well, if we factor out the t to the r, we get this smaller equation that we're going to have great interest in. And we're going to call it the characteristic equation. Because clearly, if t is not equal to 0, then this factor is not equal to 0. So what will matter is when this inside factor is equal to 0. And we're going to jump right into an example. Find two linearly independent solutions to the equation 2t squared y double prime plus y 9t y prime plus 6y is equal to 0. We have t is greater to 0, and it will become clear when we see our solution why that's necessary. So let's jump straight into the characteristic equation. So we're going to plug in a equal to 2, b equal to 9, and c equal to 6. That's what we'll see right here. Now we'll simplify that b minus a business to just become 7r. And now we're going to factorize this as we would with the auxiliary equation previously in this chapter. So we can tell since 2 times 6 is equal to 12, we would be looking for a pair of numbers that multiply to give you 12 and add to give you 7, and that's 3 and 4. So we'll separate that 7 into 4r and 3r. Again, whatever your method of factorization is fine. So we end up with 2r plus 3 times r plus 2 is equal to 0. And that gives us two solutions. R is equal to negative 3 over 2 or negative 2. And just like section 4.2, as soon as we get our two R values, we're actually done. We have y1 is equal to t to the negative 3 over 2, and y2 is equal to t to the negative 2. And that's clearly why t couldn't be equal to 0. It's because we're dividing by t in both of these instances. They're in the denominator because of that negative exponent. So these are our two linearly independent solutions. y1 is t to the negative 3 over 2, y2 is t to the negative 2. But now what do we do when the roots are either equal or complex? Well, for complex roots, remember, a general complex root is going to look like alpha plus I beta. And if we were to follow the same method as up here, we would just think our solution is t to the power of alpha plus I beta. The problem with that being it would not be real because that I is an imaginary number. So we're going to simplify this to bring this t to the alpha down as a factor. And then we're going to use the substitution because remember, e to the power of ln x is just equal to x. So, and that's what this exp means. It means e to the power of. So I'm just going to substitute t to the ib as e to the power of ln t to the ib. Well, we then use our law of logarithms to bring that ib out front as a factor. And now, based on what we did in section 4.3 with these complex numbers, we can see that the t to the alpha is unchanged, but e to the power of I beta ln t is equal to cos of beta ln t plus I sine beta ln t. And we have that, again, from 4.3, both of these factors, the imaginary and the real portions, are themselves solutions. So y1 is t to the alpha times cos of beta ln t, and y2 is equal to t to the alpha times sine of beta ln t, just like in section 4.3. Now, if we go to the equal roots question, if r is a double root, then the solutions will be y1 is equal to t to the r, but y2 will be t to the r times ln of t. Now, we've got a couple of lemmas, or a lemma and a theorem, that we're just going to go over quickly. Lemma 3, this is on page 195. If y1 and y2 are solutions to the homogeneous differential equation, y double prime plus p of ty prime plus q of ty equals 0 on an interval I, where p and q are continuous, and if the Wronskian, we mentioned this in the last video, which is equal to this discriminant, or equally, it's equal to this. If that is 0 at any point t in this interval I, then y1 and y2 are linearly dependent on I. Now, the importance of that is we were asked to find linearly independent solutions in the previous examples. So if they were to fail this test, then they would be linearly dependent and thus not solutions we're looking for. And now theorem 8, this is what's going to lead us into our next example. This is called reduction of order, and it's on page 197. If y1 is a solution to the homogeneous, so not identically 0 here. If y1 is a solution, and it can't be 0, to the homogeneous differential equation y double prime plus py prime plus qy equals 0 in an interval I, then y2 equals y1 times the integral of e to the power of the negative integral of p divided by y1 squared, is a second linearly independent solution. So if you have one solution and you're looking for another linearly independent solution, one that is not going to fall into any of the traps of this lemma about ending up as linearly dependent, then this is the manner to do it. And now we're going to try this out. We're going to say that given that 1 over t squared is a solution to y double prime plus 1 over ty prime minus 4 over t squared y equals 0, and you can check that yourself if you like. But given that that's one solution, how are we going to find another one? Use reduction of order to determine a second linearly independent solution for t greater than 0. And again, of course, t can't be equal to 0, so we had to choose either greater or less than, because it's in the denominator. Okay, well, we just bring down our equation, and we're going to start plugging things in. The known equation is t to the negative 2, so everywhere we see y1, we can just plug in t to the negative 2. I will note a typo. Little typos can get past us sometimes, but as long as we catch them. Of course, the y1 in the denominator needs to be squared. So this should actually be t to the negative 4 in the denominator, but that's fine. But let's carry on. The numerator, well, we're going to plug in what p is. P is the thing that is multiplied by y prime. So that's 1 over t. So t to the negative 1 gets plugged in here. And there's a lot of integrating, a lot of dividing to do. We just got to work from the inside out. So the first thing to do is figure out what is the integral of t to the negative 1. And we know that that's just ln of t. So we now have e to the ln of t in the numerator, and lucky for us, that's going to cancel out because e to the ln t is just equal to t. So the numerator is now just t. But now instead of dividing by t to the negative 2, we're going to divide by t to the negative 4, because that's what the equation calls for. T over t to the negative 4 is equal to t times t to the 4. So that's equal to t to the 5. So this 3 is now a 5. And now we're going to integrate t to the 5, which is clearly now 1 over 6 t to the 6. And then we'll multiply it by t to the negative 2, which will end up giving us t to the 4. So our y2 is 1 over 6 t to the 4.